Hess's law allows you to determine the enthalpy change of a reaction uh, without actually measuring anything in the lab. You can just find the standard kind of enthalpy changes for various reactions from the back of a textbook, say, and then using those reactions and their enthalpy changes, you can combine the reactions and the enthalpy changes to find the enthalpy change of the original reaction. Okay? Maybe you're provided the fact that you want to get the enthalpy change for this reaction. You were told that these numbered reactions, 1, 2, and 3, they have certain enthalpy changes. So if you can add up these numbered reactions to get the original reaction, then you can add up the enthalpy changes to get the enthalpy change of the original reaction. The thing is, though, in these numbered versions that I've written here, if you add these up right now, you will not get the desired reaction. So instead, you'll need to manipulate some of these equations first before adding some equations up to get the desired reaction. So let's kind of run through and see if we need to manipulate any of these equations. If we added this number 1 with some of the others, would we be able to get 1 carbon on the left like we will want to have? Well, yes. Here we have 1 carbon on the left, so we don't need to manipulate this equation. Next, we want to have 2 sulfurs on the left of the arrow, but right now equation number 2 has just 1 sulfur to the left of the arrow. So you will need to manipulate this equation by doubling the numbers of sulfurs. But by doubling the number of sulfurs, you'll also need to double the number of every reactant end product, and also then double the enthalpy change as well. If you have twice as much sulfur as a reactant, you'll need to have twice as much sulfur in the product to have a balanced chemical equation. And having twice as much of every reactant and product, you should have twice as much heat released as well. So by doubling everything in this reaction, we will now write out the new version. We have 2 sulfurs, here they are. We'll get 2 oxygens now, here they are. We'll get 2 sulfur dioxides, here they are. And we will now double the enthalpy change to negative 592.1 kilojoules per mole. Now go ahead and cross out that old equation. Okay. So we now have made sure that we'll have 1 carbon like we want and 2 sulfurs on the left of the arrow, but we need to check if we need to make any changes for carbon disulfide. We want 1 CS2 on the right of the arrow, but in equation number 3, we have 1 CS2 on the left of the arrow. So we will need to then not only move that CS2 to the right side, but flip the whole reaction around. If we had CS2 as a product, then we would need some sulfur in the reactant side as well. So we just flip everything around. All the reactants go to the products, and all the products go to the reactants. And flipping the reaction is going to be flipping the sign of the enthalpy change. The original reaction might have released heat, but the opposite reaction should have the opposite effect and absorb heat. So we're going to flip that whole reaction and flip the sign, and now we'll write out the new version. We had carbon dioxide on the right of the arrow, now we'll have it on the left of the arrow. 2 SO2s that were on the right are now on the left. The CS2 that was on the left is now on the right. The 3 O2s that were on the left are now on the right. And having flipped the reaction, we'll now flip the sign of the delta H. Now cross out the old version of the equation. Okay. So we want to now confirm that having made these changes, adding up the new versions of the equations will add up to the equation that we're looking for. If this version, and this version do add up and give us this, then we can add up the delta H's of these newer reactions and get the delta H of the desired reaction. So let's check if the reactions add up. So we have a carbon and oxygen on the left. Here they are. 2 sulfurs and 2 oxygens on the left. Here they are. A CO2 and 2 SO2s on the left. Here they are. And then on the right, 1 CO2 going on the right, 2 SO2s on the right, and also we'll get the CS2 and 3 O2s on the right. So boy, that's a lot of equation, a lot of things written there. So we want to simplify now. Things that are equal in amount on both sides of the equation will cancel out. So there are 1 plus 2, 3 O2s on the left of the equation, and there are 3 O2s on the right of the equation. They'll cancel. There's a CO2 on the left, there's a CO2 on the right. They'll cancel. 2 SO2s on the left, 2 SO2s on the right. They'll cancel. So all that's left now is CS2 as a product and carbon as a reactant and 2 sulfurs as reactants, all written here. That is the desired equation. So by adding up all of the delta H's of the 3 newer reactions, we are able to get now the delta H of the desired reaction. This reaction, we predict, has this enthalpy change.